This is the infamous conical tank problem, and you'll find this in almost every calculus textbook ever written. But it's a good one to see. So we've got water running into a conical tank at the rate of 9 feet cubed per minute. The tank stands down, point down, and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? And so we want to start, drawing a picture is a great way to start. We also want to just start by looking at some of the variables that we have. We know that we've got this 9 feet cubed per minute. This deals with a volume, and it's actually the rate of the volume. And we've got the height of this, and the base radius is this distance right here. This is the base of a cone, even though this cone is flipped upside down. The base radius is 5 feet. I'm going to start off by just writing the formula for the volume of a cone. So we need that. The volume of a cone is 1/3 pi r squared h. You can also, if you chose to put this on an xy axis, you could also say v equals 1/3 pi x squared y. It's up to you. I'm going to stick to leaving it as 1/3 r squared h. So I've got a picture, and I know the volume of a cone. Generally, when we do a word problem like this, we want to start off by listing some of the variables, and also stating some things that are constant throughout the problem. So we've got volume, the volume of not the volume of the actual cone, but the volume of the liquid that is in there, because as water flows in, the volume of water is going to change. We have the radius of the water level. We're going to have the depth of the water. So if I think of the water as filling up here, the h is going to be the height of the water at any given time. Water is flowing in, and you know that this height is going to change. It's going to go up as the water flows in. The radius of the water, really the radius of the surface area of the water, right? So if you think of the top of the water, is going to be a circle, but that circle is going to get larger as the water fills in. So r is the radius of the surface area of the water. R is changing, h is changing. 5 is not changing. The radius of the actual cone is 5, and the height of the actual cone is 10. So from here down to here, that's 10 feet. That doesn't change either. That's constant. So let me list again all the variables. We've got V is volume, R is your radius, H is depth. And in a related rates problem, the variables are changing with respect to time. Everything is changing with respect to time. So we'll have the rate at which the volume is changing with respect to time. And again, it's the volume of the water in the cone, dV dt. The rate at which the height is changing is dH dt. And the rate at which the radius is changing is dr dt. What we want to pay attention to is the information at the time in question. So when we think about the information at the time in question, they're asking us how fast is the water level rising when the water is 6 feet deep. Another way of asking that question is find dH dt. The water level is rising. H is changing, so dH dt when H is 6 feet. Now, we want to find dH dt when H is 6, and H is equal to 6 feet just at that moment, at one moment. That's constantly changing. We also know that dV dt is equal to 9 feet cubed per minute, and that's true throughout the problem. We've got the formula V equals 1/3 pi r squared h, and we know dV dt. We know that we're trying to find dH dt when h is equal to 6 feet, but we don't know anything about r. And so when we can, we'd like to eliminate a variable. And we can do that here using similar triangles. And you think of the height of the cone and the radius of the base of the cone has to be proportional to the height of the water and the radius of the water. Remember, the water is in the shape of a cone that is proportional to the actual conical tank. So I need to set up a relationship using that so I can eliminate a variable. I know that 5 is to 10 as R is to H, and when I solve that, if I do the cross products, I get 10R equals 5H, or R equals H over 2. Before I differentiate each side with respect to T, I want to rewrite this as V equals, instead of 1/3 pi, I'll write pi over 3. R is equal to H over 2, I'm going to square that, times H. So V is going to equal pi H cubed over 12. When you simplify, you've got H squared times H, you're going to square the 2 and multiply by the 3. Or even nicer, we can write that as V equals pi over 12 H cubed. Now remember that H equals 6 only at one moment in time, so we cannot substitute that 6 in until after we take the derivative of each side. When a value is constant throughout the whole problem, then you're allowed to use that value at the very beginning of the problem and substitute it in. But H is changing all the time, so we want to find out dH dt when H equals 6 feet. We'll differentiate with respect to time. So here we go. I'm going to have dV dt, taking the derivative of the left-hand side, is equal to 3 times pi over 12 H squared times dH dt. I want to solve for dH dt and then substitute the 6 in. And I can substitute the 6 in right now. I know dV dt is equal to 9 feet cubed. So 9 is going to be equal to 3 times pi over 12 times 6 squared times dH dt. So I'm going to simplify this. 9 equals, the 3 will cancel with the 12. This is 36. And so the 4 will cancel with the 36. I'm going to get 9 pi times dH dt. If I divide both sides by 9 pi, I end up getting, sorry I'm running out of room here, dH dt is equal to 1 over pi, and that's going to be feet per minute. Right? If you plug that in the calculator, you get the height, which is the depth of the water, is changing at, say, 0.318 feet per minute at that moment in time. So at the moment in time when the height is 6 feet, the depth of the water is changing 0.318 feet per minute.